screen share. Okay. So, my name is Samiiha Nalwoga. I'm a final year master's student at Stockholm University. I'm pursuing a master's in computer and system sciences. I hold a bachelor's degree in biomedical engineering, and I'm very passionate about data science and machine learning. That's me. So, so um, this tutorial has three parts. The first one is just basically introducing us to deep learning. I didn't really want to first go into the nitty-gritties before first giving you an overview. So someone would ask, what is deep learning? Because I believe you've been introduced to machine learning. So in simple terms, deep learning is a method that is used to extract useful patterns from data. So what do we use to carry out deep learning? We use neural networks plus optimization. What do you use to carry out deep learning? The practical, like what I'm going to show you before the end of the tutorial. We use Python. We can use Python. We can use deep learning libraries like TensorFlow, Keras, PyTorch, and so many others. So the challenges, some of the challenges we have are asking good questions and obtaining good data to perform the deep learning. And someone would ask, why now? Why are we doing deep learning right now? So we're actually carrying out deep learning because number one, there is availability of data that can be explored. Because if you know that we are in the data explosion era, we have data from all over. We have sensor data, we have text data, all that can be explored. Then the current deep learning applications, we have a face recognition, image classification, speech recognition. It can also be applied in medical diagnosis. It's used in digital assistants, for example, those ones on our phones like Siri, Alexa. Uh, then we have autonomous vehicles. Then it can also be used in making adverts. So a brief about the history of deep learning and the milestones. So if you look at this checklist, we're going to notice that deep learning was first invented or explored in 2006. And after inventing it, they used data sets like the image data set. It was utilized a lot to it was utilized a lot to perform the deep learning. I want to just quickly go through this. Then we also have the tools that have been used in deep learning. In deep learning, we have TensorFlow, we have PyTorch, we have TensorFlow, we have PyTorch, we have Theano. All those have been invented in different years and used during different years. Currently, we use a lot of TensorFlow, Keras, and PyTorch. So someone would ask, what do you mean by deep learning? So for the deep learning, I could give you an example. This is the example I have. If you look on my left, we usually have an input. For this case, we have an input, which is an image. Then we feed it into a neural network. Then the neural network, of course, is built using deep learning models like TensorFlow. Then we also have an output. So for this image, the input is 5, and our model should be able to predict that the input is 5 correctly. So this is a little piece of code. These are only 6 lines of code that we can use to build and then train a deep learning model and also use it to predict. We're going to see this further as time goes on. Let it not confuse you. So for the deep learning frameworks, the ones that I'm actually talking about in this tutorial, we have a TensorFlow and PyTorch. So TensorFlow was developed by Google, the Google AI, and PyTorch was developed by the Facebook Artificial Intelligence Group. So what I've mainly worked with, or what I mostly work with, is TensorFlow. I haven't used PyTorch, but I've read about it, and the advantages they give PyTorch is lightweight compared to TensorFlow. So if you want to build like prototype models, they always encourage you to use PyTorch, but I've used TensorFlow. And in this tutorial, you're going to use TensorFlow and Keras. So what is deep learning? So deep learning is representational learning. By that I mean, if you feed data to, let me say, a neural network, it's going to be able to get out abstractions of representations. And from those representations, it's going to be able to either do classification or regression. So if you look at this image, this side, we have the input. So this is our input data. And this is our neural network. It has 3 layers. So each of these layers has neurons. So those neurons are supposed to extract patterns from that data. So that is what deep learning is all about. So each layer here extracts something. So you're going to find here the first hidden layer will extract the edges, the second hidden layer will extract the contours and the corners, and the third hidden layer will extract the object parts. Then it shall be able to make a prediction and say that this is a cat, this is a person, this is an animal. So that is what deep learning is all about. So when you look at these images, we have Cartesian coordinates and the polar coordinates. So if you're given a task to draw a line to separate the green triangles from the blue triangle, you're going to find that it is easier to ascertain, to get a line that would differentiate uh, the green triangles from the blue triangles. I can actually draw a line here. But now when it comes to this problem, it's actually a complex problem because I'm not going to get that line that will be able to differentiate the green triangles and the blue circles. It is hard. So this is where deep learning comes in. Deep learning can actually solve these complex problems. So these ones can be solved, such problems can be solved by simple machine learning algorithms. Uh, for example, the linear SV, for example, the linear regression, it can actually solve this because it works with drawing a line, like drawing a line that can separate the two features. So why deep learning? So actually, deep learning was actually introduced because they wanted to get rid of human beings when it comes to uh, when it comes to either classification or regression. For instance, in machine learning, you would notice that you had an input, then you'll have a human to do feature extraction, then you feed those features into let me say, the model, the neural network here to do classification, that will be able to give you whether it's a car or not a car. For deep learning, the aim is to get rid of this human. For deep learning, they actually want to automate everything, whereby we don't need a human being to do the feature extraction. The human being would actually come in when it comes to the last part of labeling. So you're going to notice that with deep learning, when you increase the data, even the performance of the deep learning models is going to perform well. So the challenge of deep learning is one of them is asking the right question and know what the answer means. So deep learning, you're going to find that deep learning models are black box models. Usually it's very hard for you to find out why the neural network predicted this. So it is actually hard to ask the right questions and know what the answer means. For example, if I am able to do image classification, it doesn't mean that, for example, if the model is able to do image classification, it doesn't mean that the model is actually doing scene understanding. If the model is able to, let me say, identify that that is a cup in the house, it doesn't mean that the model knows that that is a house. So those are the challenges that are being faced with deep learning models. Another challenge is selecting, collecting, and organizing the right data to train on. I'm going to find that we have so many, when it comes to image recognition, we have so many images we can use. For instance, we have synthetic images that we can use that have been provided in the different data sets that we use to train our models. Let me say, if we're doing practice like the MNIST data sets, then we also have the photos that have been professionally taken, and also have the real world video frames. You're going to find that if you train your model on, let me say, synthetic images, it may find uh, it may be a problem for it to actually do inference in the real world. So another problem is we humans can learn from very few examples. So the deep learning models need thousands and millions of examples.
Samiiha, sorry
Yes?
to interrupt. I'm sorry to interrupt. Can you just pace down a little bit? Some people are saying you're going too fast, so
Oh,
just pace down a little bit.
okay. I'm sorry. I don't want to rush through the theory and we go to the practicals, but I'm going to read just a bit. So another problem is pure perfection. pure perception is still a major challenge when it comes to deep learning models. Reason being that if you look at these images have different lightings, different viewpoints. So it's usually hard for a deep learning, for a neural network or a deep learning algorithm to correctly identify or classify these images if it hasn't been trained on those particular images. Whereas when it comes to us human beings, it's actually easy. If I see a cat lying down like this, I can know it's a cat. But if you don't train your model with images of a cat lying like this, it may be hard for your model to actually identify the cat if it is if it is in another angle. Though right now what they're actually doing to solve such kinds of problems is they've introduced data augmentation, whereby there are so many transformations that you can use, like the vertical flip, horizontal flip, the blur, the reducing illuminations. But still, humans are still doing better than the deep learning models, the human brain. So examples of what deep learning can do. So I got this example from a tutorial from MIT. It was a very interesting tutorial. The the tutor was actually saying that, for example, in this photo, we as humans can tell that people here are laughing. Probably they were sharing something that was very funny and they're laughing, but a deep learning model cannot be able to tell the humor. It can't be able to tell what happens next. It can't be able to tell what is on people's minds. It can't be able to tell the force of gravity, like the physics. Whereas for us humans, we can be able to tell that. So deep learning, so we're going to look at the briefly looking at the training and testing process. Of course, if you have data, you have to split it into two partitions. One is the training phase and the testing phase. So here I have the input data. I input it into a learning system. Then after inputting it into a learning system, I'm able to do some kind of predictions. So after doing predictions, I can be able to ascertain the error. Uh, how well is my model performing? Because remember, this is like a supervised learning. I don't know if you talked about supervised learning, whereby you give the labels to the machine learning algorithm. So for the testing phase, so here I get new unseen data, like my machine learning model has never seen this data. I input it into the machine learning system, then it's able to generalize or make the best guess. So we go to the functionality of neural networks. You're going to see this further. So remember I said that other tools that we use in to perform deep learning are neural networks. So neural networks have a method called backpropagation. So for backpropagation, we do a forward pass and then a backward pass. So the forward pass is in this way. So for the forward pass, we get a neural network. We input our data, then the neural network is able to perform predictions. Remember, we already have the ground truth labels somewhere. So that network is able to compare the predictions with the ground truth labels, then it's able to ascertain the error rate or the loss. Then after ascertaining the loss, that is when we do the back propagation. So for the back propagation, you measure this error and then you will adjust the weights in order to minimize the loss function. I'm going to explain that further. These are just boxes. So types of predictions we can make with neural networks. We can make regression and classification. Isaac talked about regression and classification in his earlier tutorials. So an example of a regression question would be, what is the temperature going to be tomorrow? So with a regression question, I don't expect a categorical answer or a discrete answer of yes or no. Yeah, so for this case, if I ask what's the temperature going to be tomorrow, there is a range. It could be 84, it could be 90, it could be 100%. So, sorry, 100 degrees. So for a classification problem, that one deals with discrete outputs. Discretized outputs. So the question would be, will it be cold or hot tomorrow? So there you give me an answer of it's going to be hot or cold. So neural networks can do both these regression and classification. So what can we do with deep learning? So with deep learning, We can have our input in forms of numbers, in forms of vectors of numbers, in forms of sequence of numbers, in forms of a sequence of vectors of numbers. Our input data can be images. And then in the end, we're also going, and then in the end, we can also output the numbers, the vectors of numbers, the sequence, and so on and so forth. So that's what this slide is all about. So what is the inspiration? Remember I said for deep learning, the building block for deep learning is a neuron. Sorry, so we use neural networks to perform deep learning, but then the building block for a neural network is a neuron. So, so here we can see the neuron. This is how a neuron looks like, and it was inspired by the biological neural networks in our brain. So in other words, in short, with deep learning, we're trying to mimic the human brain. So that's what deep learning is all about. So here we have a neuron, and in this neuron, we have inputs to the neuron. These are the x1, x2, x0. Then then these inputs are assigned weights, the different weights. We have W0, W1, and W2. Then we attach a bias. We're going to see what the bias does. And then before this input comes out as an output, it is passed through an activation function. We're also going to see what an activation function does. So this neuron is actually trying to mimic this neuron in the brain. So remember the neuron in the brain is behind most of the intelligence in our brain. So even with deep learning, we're actually trying to work with a neuron. So this is like our intelligence, how can I call it? It's like our intelligence uh, body or something in the neural network. So what's the difference between human brain and the neural networks? So the major differences, if you look at the parameters, the human brains have over 10 million times synapses than artificial neural networks. Then we look at the topology, that is like the physical makeup. Human brains have no layers. We don't have layers in the brains, but the neural networks have layers. We're going to look at the layers. Then also, when you look at the learning algorithm, the neural networks use gradient descent. We're going to talk about what gradient descent is. Then the algorithm that the human brain uses is not known. We don't know which algorithm we use in our brains, but the brain is a very intelligent, like human brains are so intelligent. They can do so much. So when it comes to power consumption, the biological neural networks use limited power as compared to artificial neural networks. Then for the stages, the biological neural networks never cease to learn. We never cease to learn. Our brains never cease to learn. We are always learning. Then the artificial neural networks, for the artificial neural networks, we have to first train and then do the testing. We're going to see that. So this is the deep learning building block, and that is the neuron. So here we're trying to talk about the forward pass. So for the forward pass, I mean we're going to have a neuron, then you're going to have inputs to the neuron. So those inputs can be anything. They can be numbers, they can be images, they can be vectors, they can be sequence of numbers. Then after giving these inputs to the neuron, we're going to assign different weights to them. So what do the weights do? So the weights just actually show you the level of importance. A higher weight, like weights just show you the level of importance. So after attaching the weights, we're also going to attach something called the bias. It's a constant. So a bias is a constant that is used to adjust the output along with the weighted sum. So in short, the bias just helps the model to fit the given data. It allows you to shift the activation function to either right or left. So that's the use of the bias. So that is what happens in the forward pass. So after giving this neuron inputs, it will be able to assign weights to it and a bias, then it will give an output. So when it gives an output, remember our data set is labeled. You have the ground truth labels. We can be able to tell the error rate. So that's what the forward pass is all about. So in deep learning, what we do, we don't work with only one neuron. We actually stack them together. So we combine the different neurons in the different layers. So we have the input layer. This is a simple neuron, have the input layer. This is the hidden layer, and then this is the output layer. This one gives us the prediction. Then this is where we input So this is the input layer. This one allows in inputs, transfers them to the hidden layer that does some kind of math there. By that time, it is able to extract features from the data that it has been given. After extracting features, it's able to send them to the output layer that actually does the actual prediction, which could be classification problem or regression problem. So with the deep learning model, with deep learning, we mean deep. So by deep, I mean you're going to be stacking different layers, like so many layers together. So with deep learning, we are going to be moving from the simple neural network to the complex neural network. By complex, I mean you're going to be having several hidden layers. You're going to be adding on very many hidden layers. So with deep learning, the beauty with it is the more layers theoretically, the more layers you add to the network, the better the performance of the model. That is theoretical. And the reason they give is because uh, each layer you add to the network actually does some kind of feature extraction. So it's able to extract more features from the input. So this is actually just talking about what I was saying. These are the inputs, these are the neurons. So step 2, we're going to have the inputs. We attach weights to the inputs. We send them to the neuron. Then, so it's what it's doing here. So you're going to see that we're going to have this weight multiplied with the input. Okay, we're going to multiply the weight and the input for each case. So actually, we're going to find the sum, the summation. So that's what we are doing here. So we're also going to, I've been talking about activation functions. I think you heard me talking about them. What are activation functions? So these ones help the network learn complex patterns in the data. You're going to find that the layers you're going to build, you're going to be putting activation functions on them. And what do the activation functions do? They learn complex patterns in the data. How do they do it? By introducing the non-linear aspect to the neural networks. So you're going to find that the activation function is always at the end of every neuron, deciding what is to be fired to the next neuron. So the types of activation functions we have the sigmoid, we have the TANH, we have the ReLU. So we use these activation functions for different purposes. Someone would ask, why would I use a ReLU and not a TANH and not use a sigmoid? Most of the work I've worked with, I've actually been using ReLUs a lot, and the answer and the reason they give is they have reducing vanishing gradients. By that I mean, if you're trying to do like the propagated error for vanishing gradients, I mean that the propagated error usually increases or decreases exponentially with if you use sigmoid or tan. So that's why I've used ReLUs a lot. Then we also have the loss function. So what's the use of the loss function? Remember I told you that with deep learning, we usually have, okay, for instance, if we have predicted values, we're always going to have the ground truth labels. So for us to know how well our model is performing, how good is it performing, how bad is it performing, is it deviating away from what is the deviation? We use a loss function. So the loss function helps us quantify the gap between the prediction and the ground truth. So for regression, the loss function we usually use, the commonly used one is the mean squared error, and this equation shows you how to get the mean squared error. Then, so we also have classification where we use the cross entropy loss. This equation shows you how to get the cross entropy loss, but basically it's just subtracting what has been predicted minus the ground truth. That is it in short. So this is the concept of backpropagation. So like I said, this is our neural network. These are our neurons, these are inputs, this is our output. So we give our neural network, our neural network inputs. Then after giving it inputs, it will assign weights and a bias. We now know what a bias does and what the weights are used for. Then it will send it to the output layer. So the output layer is the one that will make the actual predictions, whether it is true or false, whether it is a 1 or 0. That is in case of classification, in case it's a classification problem. Then For the back propagation, what we mean is after giving the predictions, we're going to get those predictions and then compare them and match them with the ground truth labels. So after comparing them, we'll be able to get the error. So after getting the error, we're going to do what we call back propagation using gradient descent. So for back propagation, I mean that we're going to get this error and then differentiate it. By differentiating, I mean I find that the derivative with respect to the weights that it came with. So that will be the gradient. So we shall do that when it comes to every layer. Sorry, well, we shall do that on every layer. So that's what they call gradient descent. Like it keeps on diminishing, like reducing the loss. So that is what the back propagation is all about, some kind of differentiation with respect to the weight. So problems of deep neural networks, deep learning, one of the biggest problem with deep learning is overfitting. So overfitting, I mean that the classifier or the algorithms performed so well on the training set and then it performs poorly on the test set. And how do we evaluate the performance? We evaluate the performance by looking at the loss function. We could use the accuracy, but we use the loss function because accuracy is very misleading. So if the loss function is low on the training set, by the loss function I mean the error, if the error is low on the training set and high on the test set, that is a sign of overfitting. It means that the model is performing so well on the training set and then performing poorly on the test set. And yet our aim is for us to get a model that performs well on the test set. Like our target is the test set. So what are the ways that are currently being used to come overfitting? We have radialization. So we have different techniques. We have early stopping. I've used that before. That is like early stopping. By early stopping, I mean uh, stopping the training of a model at the point where by there is no improvements improvement in performance. So we usually do that by getting a training set, and then after getting the training set, we also get a subset of the training set called the validation set. So that's what we use to validate the performance. But that is something that is not in the fundamentals. So we can also use dropout. They use it a lot. So for dropout, we mean you randomly remove some nodes in the network. Okay, you don't physically get them and plug them out, but you just keep on deactivating them in the network. That also helps with overcoming the problem of overfitting. Then you also have batch normalization. It's used a lot in so many deep learning, in so many neural networks. So what does that mean? So for that, we just normalize. By normalize, I mean normalizing is just getting a standard. Uh, Normalizing is just let me say if I have a range of values from, let me say, 0 to 20, I could normalize them, and then I'm like I want them to lie between 0 to 1 by finding the standard deviation and the mean. So here you just normalize the hidden layer inputs to mini batch mean and variance. So what does it do? It reduces the impact of the earlier layers on the later layers. So that's the introduction I had in theory before we dive into the practicals. I don't know if anyone has a question before I continue.
Yes, there are a couple of questions. There are a couple of questions in the chat. There are actually three of them, but one of them is good to go. So the first one, I didn't understand point number two. I don't know point number two of what. Maybe Matovu can expound on this so that we have some context. And then Patricia is asking, so ReLU does not propagate errors. So yeah, I think these are the two questions you can take.
Okay, ReLU doesn't propagate errors. I don't get her question. I didn't say ReLU propagates errors. I said we apply activation functions every time we're working with neural networks, and I said that the reason why we apply them is because activation functions introduce the non-linear aspect to neural networks, and by introducing that non-linear aspect, it's able to extract complex patterns in the data. So maybe she was, I don't know, I don't understand her question. Maybe she meant the vanishing gradients. What I meant by that, can she speak up? And I don't understand.
No, it
Because
is fine.
errors.
I think it's okay. We can proceed. Let us proceed with the practical side of things now.
Okay. So can you still see my screen, or I must have shared a tab.
We can still see the same screen, the presentation.
Okay. So new share this. So can you see my screen? Can you see the new
Yes.
screen, that Jupyter notebook? So here, we are trying to build a simple neural network using KRAS that we're going to use to classify if a patient has diabetes or not. So in this tutorial, we're going to be using a Pima Indians Onset dataset. You can get it on Kaggle. I left links there. And this is a standard machine learning dataset from the UCI machine learning repository. So it describes patient medical record data for Pima Indians and whether they had an onset of diabetes within the 5 years. So as such, it's a binary classification problem. I'm going to visualize the data set, then you're going to be able to see what I'm talking about. So all of the input variables that describe each patient are numerical, which is good for us because neural networks accept a numerical input and output values, and ideal for, and this is actually very ideal.
Samiiha,
Yeah.
sorry to disturb you. I think Musa and Patricia, they have both come back. Musa is saying, when you say that machine learning includes the machine, and for deep learning, we are eliminating the machine, which kind of a machine exactly, since you can't do away with the computer when dealing with deep learning?
Okay,
That
I
is a
think
question from...
I think Musa got me
sorry?
wrongly. He said with deep learning, we're trying to deal with the human, not the machine. That's what I said, because you're going to find in machine learning, we need to get a human to do feature extraction. For with deep learning, we don't need a human to do feature extraction. Like the algorithm is able to do that on its own. So that's what I meant. I didn't say machine.
Okay. Then Patricia is saying her question in regard to above, her earlier question was, so ReLU does not propagate errors. But in reference to that, she says, you said sigmoid and turn functions propagate errors. So you prefer ReLU. That's why she actually asked the question.
I said that they have a problem of
Do
vanishing
you get it?
gradients, not propagating errors. Yes, like that's what I said. Because propagating errors is something that is done by a neural network. I was explaining back propagation and how it occurs. So what ReLU and TAN do, they are not involved in propagating errors. Like I said, they just help us introduce the aspect of linear, the aspect of non-linearity. And by so doing, we're able to extract complex features from the given data. That is what I said. Maybe I should talk about what I mean by vanishing gradient. By vanishing gradient, I mean that the error that is back propagated keeps on increasing and decreasing exponentially. It keeps on fluctuating. Like that's what I mean by vanishing gradient. I don't know if I've answered her question.
I think that's good enough. We only have 50 minutes for the practical side of things. I think you can carry on now.
Okay. So what you're going to use is Keras. What is Keras? Keras is a free open source. These are deep learning libraries that help us with abstracting all the technicalities when you're trying to build deep learning models. These ones just help us, like they're kind of like helper libraries that are provided freely by Python. So this is what Keras does. I try to give you a little bit of the overview and the background of what it does. So here I'm trying to show you how to install Keras. In case you try to run any of the notebooks and then it throws an error of install Keras, you can use pip to install Keras. yeah, and then if you need to upgrade, I've written all that here, but that's not the reason why I'm here. So here we have the first step we do is to load our data set. So you can see the first step is to define functions and classes we intend to use in this tutorial. So we're also going to use a Numpy library. I'm sure the previous speaker talked about Numpy and pandas. So we're going to use a Numpy library to load our data set, and we'll use two classes from the Keras library to define our model. So here I'm going to import Keras. How do you import that library? That library that you're going to use to build your neural networks. You just you just write import Keras. There you'll be able to import the library. Then you're also going to import pandas. So the reason why I imported pandas, I'm sure you've seen it there. I'm just trying to import pandas because I want to use pandas to 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 load my data set. I use pandas, but you can also use NumPy. So then when it comes to loading the data set, I just say, I just give it a name, variable name dataset is equal to pd.read CSV. Then I give the name of the data set. I'm using my data set is in a CSV format. Here I'm just trying to put commas, like separate everything in the data set using commas. That's what this means. So here I'm trying to visualize the data set. So this is what I was talking about. So you're going to see that we have we have 7 features. One is pregnancy, glucose, blood pressure, skin thickness, insulin, BMI, diabetes, age, and then this is our output. These are our target labels. So if someone has uh, 6, let me say as the pregnancy, okay, these were just coded. They're just encoded. And glucose has 148, and then pressure 72, blah blah blah. The output should be 1. It continues. If someone has, let me say, 185, 66, and the output should be 0. So like I said in my previous tutorial, it is key to have good data when you're going to be performing, let me say, deep learning. So what I did here, I was trying to do some kind of visualizations with my data. I visualized it, but this wasn't enough because this gave me just a few rows. So I wanted to check if there are any missing values, because usually you're going to find that if you're working with the real life data sets are data sets that you have to clean yourself. This is a data set that I was able to pick from Kaggle, so everything was done. There are no missing values, but if you're working with real life data sets, you're going to find missing values. You're going to find so many things. So you always have to first visualize and then do some kind of data cleaning. So here, what I was trying to do was I was trying to check for the missing values by calling the isNull function. Then I was able to find out that there is no missing value. So it was like a go ahead continue. So what I had to do, the next step was to split my data set into X and Y. So remember, X are the input, which are the features, then the Y are the ground truth labels, or the actual labels. So that's what I was trying to do here. So someone may ask what this slicing is doing. So here I was just trying to pick the first 7 columns, because remember the last column is the one that contains the labels. So I have, so these are my features. Here I'm trying to visualize my features. Then here I have my labels. I'm also trying to visualize my labels. You see they are the same, 1 or 0. They are they're discretized, 1 or 0. So this is a classification problem. So after splitting, so after splitting the data set into X and Y, I had to come and split the data set and create a training set and a test set. So someone would ask, what's the use of having a training set and a test set? Can't I train and test from the same data set? That is not advisable, because that is like cheating. It's like you're trying to train the model on a given data set, and then you're trying to test it. Like the model has already seen those examples. So that's why we split it. So that's why we split the data set into training and test. For training, we give it the class labels, like the ground truth labels, like it's trying to learn, but it's learning based on the labels or the ground truth labels you're giving it. Then for that test, like those are new examples. The model has never seen it. So we want to see if it can be able to generalize, to do inference. So this is a whole lot of here we're trying to define, so I was trying to say in Keras, models are defined as a sequence of layers. So we create a sequential model and keep on stacking layers together one at a time until we get our desired network architecture. So we should ensure that the input layer has the right number of input features. So this can be specified when creating the first layer with the input dim argument and setting it to 8 for the 8 input variables. So you could read through this in your free time. So how do we know the number? So this is a very good question that actually came up sometimes. Someone was asking me this question. How do we know the number of layers and their types? So this is a very good, but also a challenging question to answer. So the best network structure is formed through a process called try and error experimentation. So generally you need a network large enough to capture the structure of the problem. I think if I'm to reiterate, I told you that with deep learning models, the deeper the model, the better the performance. The deeper by the deeper the model, I mean the more layers I have in the model, the better my model is going to perform. Why? Because each layer is going to be able to extract, let me say, different features. So the more layers I have, the more features I'm going to be able to extract, and therefore the better performance, the better my model will perform. So in this example, we'll use a fully connected network structure with 3 layers. So we have a fully connected layer. So fully connected layers, I use dense. So dense represents a fully connected layer. So fully connected layers are defined using the dense class. We can specify the number of neurons or nodes in the layer as the first argument and specify the activation function using the activation argument. So we'll use the rectified linear unit activation function called ReLU on the first 2 layers and sigmoid function in the output layer. So it is used, so let's go to the code. So this is our model. The first thing we do is to say model is equal to sequential. So here I'm trying to tell, so here I'm trying to mean that my model is going to be in a sequence form. Like I'm going to have layers, but they're going to be in a sequence form. They're going to be in a sequential form. So after calling model is equal to sequential, I add a model.add dense. So like I said, dense is a fully connected layer. So I will state the number of neurons I want in my layer. So with this is also experimentation. And then the input DM, the input DM shows the size of the input. Remember, we said we have 8 features, so the size of the input has to be 8, and the activation is ReLU. So we go to the next layer. How many neurons do we want on the layer? We want 8 for this case. Then the activation is going to be ReLU still. Then model.add dense 1. Then here we are going to go. Here we are only using 1 neuron, and then the activation is sigmoid. So why are we using sigmoid? You're going to find that if you gain experience in deep learning, if you're dealing with a binary classification problem, you always use sigmoid layer in your output layer. Like then if you're dealing with the multi-classification problem, that's why you look at the softmax activation function. You always put it there beneath. So after defining our model, we need to compile it. So compiling, the model.compile actually lets us use other parameters. Okay, like feed other parameters into our model. For instance, the loss, the optimizer, and the matrix. Like I said, what does the loss do? The loss is just there to actually show us the performance of our model. The loss just shows us the error rate of our model. So it's always good for us to have a low loss value. Then what does the optimizer do? I know probably you've seen this optimizer. We have so many. We have Adam, we have SGD. I usually use Adam a lot. And this is also like, for you to know what optimizer to use, it's also experimentation, depending on the network you have. So the optimizer, what it does, it just keeps on changing the weights and the learning rates. It keeps on changing them so that the loss keeps on getting lower. Then the metrics you can use is accuracy. That's what you're going to use for this tutorial. Though, like I said, accuracy is not the best performance metric to use because it's very misleading. Then after compiling, the last step is to fit. Fit, by fit, I mean I'm trying to train my model. So what do you train it on? So if I want to train my model, I call the model and the .fit function, and inside there, the arguments I put are the xtrain. So xtrain is the training set, and then I give it the labels. Remember, it's going to be training, but it has to have like a reference point. So I train it, then I give it the labels. So for this case, I trained it using 150 epochs, but you can use 150 epochs and a batch size of 10. So someone recently asked me, how do you know how many epochs to use when you're training your model? That's also that one is not through experiment. Okay, that's not through trial and error experimentation. Actually, how do you know? You can tell by actually using the early stoppage. So by the early stoppage, because you're going to find that the more you keep on training these models, they will always reach an optimum, and then they will start overfitting. So you always have to know which epochs to stop on. But how do you know? By using radialization, and one of the ways to do that is using early stopping. So after a training, you're going to fit. After fitting that training, you're going to evaluate your model. So what do you put? How do you evaluate your model? You're going to call the evaluate function, and what arguments are you going to put? You're going to use the x test and the y test. So X test is these are the unseen features. Therefore, we want our model to be able to make predictions. So the reason why I put the Y test is not for the model to learn, because right now the model has finished learning. It has already gained knowledge. So what it's trying to do is to make predictions on the X test. Then this Y test is just these are just the ground truth labels that we are going to use to ascertain how well our model is performing. So this will help us come up with like a loss function. How well is our model performing? Is it deviating away? What is the error rate? So here we're going to come and so after training and evaluating the performance of your model, it's now time to start making predictions using your model. So for this example, we can use train model to generate predictions on the training data set, pretending it is a new. So for this case, what I did is not advisable, because I did predictions on the same data set, but because I didn't have a separate data set to use, but what I should have done is probably I should have split it into one for prediction and then one for training and testing, but I didn't do that. So here I pretended that data set contains unseen, let me say, examples. So I came and did predictions on it. How do you do it? So making predictions is not a hard task. You just call the predict function on the model. That's what we call it here. And since we're using a sigmoid activation function on the output layer, the prediction will be a probability in the range of 0 and 1. So we can call the predict classes function on the model to predict crisp classes. By that I mean classes that are rounded off, because we'll never have a probability that is sorry. So crisp classes, so that means that we are going to be rounding off so that they lie between 0 and 1. So after making the predictions, so here we're going to say model.predict classes X. So here we're trying to, what I was trying to do is I was trying to predict and then make a comparison and see if my model got it right or wrong. So let's first look at the accuracy we got for our model. So the accuracy we got after training, after evaluating, we got the loss was 0.59 and the accuracy is 73.4%. So when we came and predicted, we found out that for the in a range of 10 cases, here it gave us 1, but the expected answer was 1, so it got this right. Here it gave us 0, and the expected answer was 0, so it got this right. This was right. This was wrong. It gave us 0, but the expected answer was 1. So this was right. This was wrong. It gave us 0, and the expected answer was 1, so on and so forth. So that is the simple neural network using Keras. Here we're actually using Keras. I have another tutorial whereby we're going to be using TensorFlow. I don't know if there are any questions regarding this before I continue.
We have two questions on the chart, one by Nyako Samuel and another one from Musa. Samuel is asking, why have you used sigmoid in the last layer? Because the first two were Relu. So that was upstairs. Yeah, it should be around. No. It should come back down, I think. Yeah. So
Here.
you. Yeah. So he wants to find out why have you used sigmoid instead of Relu, and you actually used two. The first two were in Relu.
Okay. So I used Relu. Like I said, if I'm to reiterate, I remember I previously said that if you have a binary classification problem, by binary I mean uh, your output is either 1 or 0, yes or no. Your activation function in the output layer is always sigmoid. You always use sigmoid. But if you have a multi-classification, the activation function in your output layer is softmax. So the reason why I've used there is no problem in you interchanging and using Relu here, but you cannot use Relu here in the last layer because the problem I'm dealing with is a binary classification problem, 1 or 0. So that's why I take sigmoid and I don't use Relu. I hope I've answered you correctly.
Okay, I think he will clarify in case there are any other more questions he wants to tally to that. Somebody's asking, before Musa, there is something that you need to address. I think that one we can address real quick. Somebody's asking, what is an epoch?
So an epoch is like it's like an epoch is like a cycle, like during training, like one full cycle. So here I have here I specified 150 epochs, but then now this is the first cycle of 150 cycles. Like it's a full cycle during training, like a full cycle during training, whereby my algorithms will loop through the training data set. It's like a full cycle of training. That's an epoch. A full cycle of training. Then I have Epoch 2, that's a second, a second full cycle of training. Then Epoch 3 is another third cycle of training, a full cycle of training, whereby the algorithm is able to loop through or go through the training data set.
Maybe, I don't know if can we, Samiiha, can you define maybe from because I know what an epoch is, but I would like you to define it from a standpoint where you're actually looking at an epoch vis-a-vis a batch, vis-a-vis an iteration. So maybe we can get the difference properly.
So for an epoch, how I would understand it is, remember, I give my neural network data, then it's the algorithm is able to loop through, let me say, run through all the examples in my training data set. So that is that is an epoch, like that cycle. It loop through, it run through all the examples of my data set. That will be the first epoch. Then I don't know if I make sense. I don't know how best to explain it. I don't know if someone can help me better explain it to someone, okay, to people. But it's like a full cycle of training where my algorithm loops through or goes through all the examples in my training set. So that will be the first epoch. It does that again, second epoch. It does that again, that will be the third cycle. It does that again, fourth cycle. Like it's doing that, but while it's doing that, let me say the different neurons are able to extract features during all those cycles. I don't know if I make sense. I don't know how best to explain it for him to understand.
Okay. Yeah. So I think that was clear because some people always confuse the three aspects. An epoch basically is the entire data set that will pass forward and backward through the neural network, but it should be only at least once. Then when you're defining the iterations, you actually you're looking at the number of batches. So I think I need to explain what a batch size is in that regard, because a batch size is basically the total number of how many trainings or training examples that you can present in a single batch. And then in the same regard, an iteration is now the number of batches that you need to complete one epoch. So in basic essence, if you're looking at some underfittings to gain the optimum value, you're going to expect that to fit into context, you actually have to work with an epoch to get to a batch size and to also to get to an iteration. I think, Samiiha, well done with the explanation. I was just expounding
Yeah,
on
it's
it.
okay. It's good
Uh,
data.
Yeah. Then we have another question from Musa. It was the second question, actually. He's asking, can testing data be manipulated from training data, or it should contain different data? Can
Testing
testing
data
data be manipulated?
manipulated from training data.
Yes.
No, testing data should not be manipulated from training data. It should be entirely new data. And that's why we split it. We do that splitting. We get a data set, then a full data set, then split into training and then test. Whatever is in the train should not be in the test. That is okay, it helps with the ascertaining, like let me say assessing, or with the making a better evaluation of the situation. Because if I use what I trained the model in the testing data set, it will be cheating. Like my testing accuracy may be high because the model has already seen those examples in the trained data set. So it should be entirely new unseen data.
Okay. We have another question from Balde. I'm not so sure if she or he is using accuracy telling us how good the model performs, or these are other ways we should try. Is using accuracy telling us how good the model performs, or there are other ways we should try?
Uh, like I said, I think I've been saying this before, accuracy is just showing us the fraction of examples that have accurately been, let me say, should I use accurately? Like the fraction of examples that have been predicted accurately, but it is not the best evaluation metric to use. I can say this. It is what we're using right now because these are just the basics. But as you dive deep into deep learning and let me say machine learning, you're going to find that there are better evaluation metrics. For example, you're going to look at precision. That's why we look at precision. That's why we look at average recall. That's why we look at rock area under the curve, receive operating curve, rock area under the curve. So accuracy is not the best because it can be misleading, especially if we have, let me say, an imbalanced data set. It can be misleading because with accuracy, you're going to find that if you have an imbalanced data set, I think it happened to me during my, I'm currently finalizing with my thesis. I worked with an imbalanced data set and I was using accuracy as a an evaluation of performance measure. And what I found was that my model was giving me 80% accuracy, but when I went deep to investigate if this model was actually performing well, I found out that it was biased towards the majority class and then poorly performing when it came to the minority class. So accuracy is not the best. It's not the best to use. But for starters, you can use it. Like if you're just getting introduced to neural networks and deep learning, it's good to start with it. But as you dive deep, you're going to find out that it's not the best metric to use.
Okay. Please, if you know you are the ones who have asked the questions, you can affirm if you've understood the explanation, or if you want more information in the same regard. Please feel free to post your affirmation. Abdallah is asking, I would like to see how you would load the libraries and the datasets. I would like to
Yeah.
see how you will load the libraries and the datasets.
Okay, so we go back to this cell that has the libraries. So for loading libraries, usually importing libraries, you just in Python you just import, then you use import and then the name of the library. So we are using import chars, import pandas as a PD. This is just like an object that I just used, but you could say import pandas. Okay, I used as PD because I didn't want to come here and write a full statement, pandas.read underscore CSV. So that's why I said import pandas as PD. So when it comes to loading the dataset, I don't have to say pandas. I will just say PD. So if you're trying to load the dataset, what I used pandas, but you can use NumPy. So if you're to use pandas, you use pd.read CSV, then you give it the name of the CSV. This is diabetes.csv. That's it. That's how you load the libraries and then the dataset. Then here I'm trying to visualize. I just call the dataset and I'm able to see what's in the dataset. That's what I was actually trying to do here.
Okay, thank you very much, Ms. Samiiha. The next question. So in a multi-class classification, are we going to use a single neuron in the output layer when using softmax activation function?
No, we don't have to use a single neuron. Like I said, these things of neurons, what usually happens, it's more of trial and error, but we cannot use a single neuron. It's more of like just keep on doing trial and error and see how your model is performing, but you wouldn't use a single neuron. It's more of trial and error. That's what you do. Okay, that's what I mainly do when I'm trying to, let me say, build my neural networks. I try 20 neurons, let me say, in the first layer, and okay, in the hidden layer, I keep on reducing them. From 20, I go to 18. From 18, I go to 16. I just keep on reducing them. I just want to see how the model is performing. Is the performance improving? So it depends on the problem you're dealing with. So I think you probably would have to first look at your data set for you to know, but I do not think it will be one. It's trial and error. You just keep on playing around with the neurons. You just keep on playing around with the neurons. But usually it's you just keep on reducing them.
Next question from Ariana Henry. How comes the execution time for almost all data sets is the same? How comes the execution time for almost all data sets is the same?
I don't get that question. Which data sets? All the data sets in the real world, or I don't think.
Okay,
I
probably
don't.
what we have, but Rihona can expound on this question because we have limited time. As he's expounding this question, I would like to go to the next question. In case I test my data, this is from Marvin Frost. In case I test my data and I get a poor prediction, how can I improve my prediction with the same data set? In case I test my data and I get a poor
The poor
prediction, how
prediction.
can I improve my prediction with the same data set?
Yeah, so like I said, you first of all need to find out why your model is performing poorly. So usually models perform poorly because of overfitting. So if it's overfitting, then you have to look at the regularization techniques that you could use to stop overfitting. Like I said, you could use the dropout layers. That's when you'd introduce the dropout layers. That's when you would uh, probably introduce the batch normalization layers. They also help with the overfitting, and sometimes even playing around with these metrics actually does a lot of good. For example, if you change the optimizer, you could find that I've used Adam, but Adam is not the appropriate optimizer to use when it comes to my problems. I would have to use like SGD or RMP probe. Yeah, so you just have to keep on playing around with the metrics. Sometimes you're going to find that I'm using binary cross entropy. Okay, for this case, I have to use binary cross entropy because I'm dealing with a binary classification problem, but you could find there are beta loss functions to use in order to improve the performance of your model. Secondly, so with deep learning, one of the ways to improve performance is also to improve the variability of your data set and improve the size of your data set. So you could adopt data augmentation techniques that would help you artificially increase the size of your data set, because it's theoretically proven that if you increase the size of your data set, even the performance of your model usually increases. So those are some of the tips that I could give you for now.
Okay. Remember, people, we have Topia. So if you have a lot more questions, we have a 1 hour, 30 minutes break for lunch. So during that time, I'm sure our facilitator will put lunch aside. Just kidding.
Yeah, so I wanted to go back to sorry, this question of would I use one if I had a multi-class? Yeah, sorry, I want to clarify. Where is it? Yeah, if you had a multi-classification problem, I wouldn't use one here because let me say if my multi-classification if it was a 10, like if I was dealing with a problem whereby I had to predict 10 classes, the dense layer here would be 10. I'm sorry, let me clarify, it would be 10. If it was 3, the dense layer here would be 3.
Okay, now.
But I have another, Eugene, I have another one for image classification where I use
Okay,
TensorFlow. This is Keras. I
okay,
could
okay. Cool, cool.
quickly go through it.
Okay,
Yeah.
let's go through it, please.
Uh, Stop screen share. So let's quickly go through one of TensorFlow. This is image classification. The other one was just text. Sorry, it wasn't text, it was numeric data. So here I wanted to go through one that actually does the actual image classification. My colleague Benjamin will clarify more when it comes to CNNs. I use the CNN here, simple CNN, but he will give you more information about the pooling layers, the max pooling layers, the convolutional layers, and what they do. But I just wanted to show you because CNN is also an example of a deep it's a deep learning classifier. So here the task is to build a convolutional neural network classifier to classify images of handwritten digits of the MNIST datasets. We shall be testing a CNN classifier on a high resolution handwritten digits not picked from the dataset. So previously, remember we were doing predictions based on on the datasets we used to train and test on which is wrong. But here we actually got uh, let me say we're able to get handwritten digits from a different data set. So here giving an overview of what the MNIST dataset contains. It contains 70K grayscale images of handwritten digits at a resolution of 28 by 28 pixels. So our goal is to take one of these images as input and predict the most likely digit contained in the image along with the relative confidence in this prediction. So now we have to import the libraries and load the dataset. Remember, previously we've been using Keras, but here we're going to use TensorFlow and Keras combined. TensorFlow is an open source library for performing fast numerical computations. It was created by Google and released under that open source license. So the API is nominally for Python programming, of course. So let's run into how to install TensorFlow. You just use a pip install TensorFlow. That's if you have like a SciPy running environment. Use a pip install TensorFlow. And more information on how to install, upgrade, and all that about TensorFlow, you can find it here. I left a link. So here we're going to import the required libraries for deep learning. So here we're going to import TensorFlow as TF. I think I explained why I'm using TF and not, yeah, I'm using TF because when I'm using TensorFlow, I don't want to write the full TensorFlow word. I want to use the short form as TF. So I also imported NumPy as NP. It also helps in numerical computations. Also imported Keras. So these libraries that I got from a certain blog that was that gave us more info on how to make these animated digits. You see it below because that's the one that we're going to use to test our to make predictions, to test if our CNN is actually doing a good job when it comes to generalization. So here, how do we load the data set? So the MNIST data set, you can load it using, so we call it, so sorry, MNIST is equal to TF because it's actually a TensorFlow data set. So we just call it MNIST is equal to tf.keras.dataset.mnist. So we're getting it from TensorFlow. So here, that's where we do the splitting, split your data into train and test. Then here I wanted to check to see how the images look like. So here you import matplotlib.pyplot as PLT. So matplotlib helps you with visualizations as well as Seaborn. So you use these a lot, Seaborn and matplotlib. When it comes to plotting graphs, visualizations, these are libraries that you use. Then here I was just trying to plt.imsure. I'm just trying to visualize what is at what image is at index 0 in the training set. So it's a 5. So this is how the images look like in the data set. So image preprocessing, like I said, before you feed your data into the neural network, you always have to do some kind of data cleaning. No, for images, you do image preprocessing. So here I come and reshaping the array. Here I was just trying to do some kind of reshaping of the array so that it can work with the Keras API. So here you reshape the images to specify it's a single channel. Remember, it's 28 by 28, a single channel. So the input shape is 28 by 28 and it's a single channel. You're just trying to specify that. Then here, just trying to make sure that the values are float. Then here I was trying to do some kind of normalization, still image processing. So here after doing that, I came here and I wanted to visualize more. I wanted to see more of the image. I wanted to see 5 in that range. I wanted to see how they look like. So this is how randomly picked 5 look like. This is how the images look like in the data set. So here I come to building, when it comes to building the model, I'm going to build a Keras model. So I'll say from Keras.models import sequential. I think I told you what sequential means. Sequential means that I'm trying to, my network is being built like in like a sequential manner. I have layers, but they are in a sequential manner. Then here, this is my input layer. I add a max pooling. Benjamin will clarify more about this. I think his talk is tomorrow. You should not miss out on it. He will talk about convolutional neural networks and what each of these layers do. So it does. Then I have a dense layer, specify the number of neurons. Then I have a dropout layer. I thought I talked about this. But what the dropout layer does is to reduce overfitting. It's a form of visualization. Then at the dense 10, this is the question that someone asked me previously. So here I'm using 10 because if you go back here, okay, I'm using 10 because my labels, like I have 10 labels to predict, and the labels start from 0 to 9. So that's why I use 10. So the number of neurons to use in the last layer, how to know which number to use, let me say 10. I'm using 10 because my prediction, because I have 10 classes to predict. If I had 9 classes to predict, I would use 9. If I had 3 classes to predict, my dense layer would be 3. I would use 3 here. And like I told you, here the softmax layer I'm using, sorry, here the activation, here I'm using the activation function. The activation function I'm using here is softmax because it's a multi-class classification. It's not binary classification, it's multi, it's 10 classes, not 2. So here I do the compiling. My optimizer is Adam. My loss, I'm using the sparse categorical cross entropy. In my previous example, I used the binary cross entropy because I was dealing with a binary classification, but because I'm dealing with a multi-class, I'm using sparse categorical entropy. And had I used binary, it would have thrown an error. You meet those errors along the way. So the metrics I'm using here are accuracy, though not the best, but that's what I'm using because it's it's the start. I'm like introducing you to the basics or fundamentals of deep learning. So model.fit, we saw previously model.fit, it just helps us train our model on the data set. So what I give it is the X train, and then I also give it the Y train to, so the Y train are the labels used for comparison. I'm just, okay, like I just want to compare how my model is performing. So the epochs here, I'll use 10. So when it comes to evaluation, when I, after training, the accuracy was at 99.34% on the training set. And after evaluating, the accuracy was at 98. But like I said, I don't usually focus on the accuracy. I usually like looking at the loss because it means more. The loss shows me how my model is performing, how is it deviating, like what's the error rate. So here the loss is 0.05. So when it comes to making predictions, I picked this interesting code from some blog. I think I put it here. If you want to know more about the code, you can go to the blog and find out what the guy was actually doing. He was doing some interesting stuff. Was using open CVs and stuff. So this is the code that is generating the video that I want to make predictions on. So if I run the code, you can see that my model is able to predict 4, 5, it shows you 6, it shows you 7, it shows you 8. Like that is what my neural network is predicting. Like whenever it looks at, let me say, a value being displayed in the video, is able to show you that, oh, this is a 0. It's able to say, yeah, this is a 1, that's a 2, it's 3, it's a 4, it's a 5, it's a 6, it's a 7, it's a 8, and then 9, and so on and so forth. So that's what I had for you. In case you have any questions, feel free to contact me. And thank you for listening.
Okay, well done, Samiiha. Well done, well done. Thank you for that wonderful presentation. We have 5 minutes to 1 exactly, but I think we can tackle maybe 2 or 3 questions that we have. Then I'll also advise that you log into that Topia that I've shared, topia.io stroke Indaba, and you can easily meet with Samiiha face to face, and you have a discussion there right away. So we have a couple of questions that we need to resolve. Just a second, please. Okay, Samiiha, we have a couple of questions that I think we can easily go through real quick. I would like her to explain more on how to choose an ideal number for an epoch. That is from Matovo Moses.
Okay.
How to
Can I
choose
focus
an
on that
ideal
one?
number for, yeah. How to choose an
Yeah.
ideal number for an epoch.
Epoch. Yeah. So you can use a regularization technique called early stopping. So by early stopping, let me explain to you what early stopping means. So like I said, if you keep on training your neural network, of course, the performance is going to improve, but and then time is going to reach whereby your model is going to start overfitting because you overtraining it. So it will start overfitting. So there has to be that optimum, like that point whereby your model performs best. So that's when the early stopping comes in. So for early stopping, I mean you're going to stop training your model at the point that your model stops sorry, at the point that the performance of your model stops improving. So let me say, if you're looking like, let me say at a loss function, remember the loss function is supposed to decrease, so it will decrease up to a certain point, then it will keep on increasing. So it means that for early stopping, I will have to stop training of to stop the training process of that model at that particular point where the loss, let me say, the loss value is the lowest. So that's the early stopping. So it means that I'll stop training at that particular epoch. So that's why you're going to look at callbacks and all that kind of stuff, but that is some other complex stuff. But I could take you through it during the break if you want to see how it actually works, because I believe it will make better sense if you see how it works. But that is how you know how to stop, like use the early stopping technique. You stop training your model at the point that your model stop at the point that the performance of your model stops improving. So that epoch is the one that you stop on. Yep.
Thank you very much, Samiiha, for that, for your presentation. I really appreciate the time that you put in. I know we have some questions that are still ongoing about the type of data set that is required vis-a-vis vis-a-vis the batch size and things like that. But I think we can save that for I think we can save that for a face-to-face with Samiha. Just log on to topia.io / Indaba, and you should be able to see some people also there. You can link up, you can get to know each other, and so on and so forth. And for the material, we have a shared Google folder, which is also shared right here. So you can easily get material that was shared by Mr. Alan and Isaac early in the morning. We are going to also update with Samiha and Claire's content in the near future, so that you can actually be able to access all these things. So just feel free, get back to us as soon as possible so that we can support you through this event. So right now, we are going for a lunch break for the next 1 hour and 30 minutes. And we shall be back at exactly 2:30 to begin with our next trainer, facilitator, Madam Claire. So in the meantime, we can be having the lunch as we also have a chat via topia.io / Indaba. See you all at 2:30 sharp.